rapporteur de l'Université de Grenoble, Alan Chalmers de l'Université de Warwick, Marcello Bertalmio de l'Université de PU Fabra, je sais pas si je prononce ça, Nicolas Bonnel, chargé de recherche CNRS au LIRIS, Éric Renard, chercheur à Technicolor. Les encadrants, les vrais, enfin les vrais, Remi, Cozot et Olivier le Meur, et puis Kadi, Bouatouch, le Rennes, tous. Et puis moi-même, Éric Marchand, qui vais présider ce jeu. Voilà. Donc, Hristina, tu as 45 minutes.
Thank you. Good morning, everybody. I would first like to thank the committee members for coming to my defense. It's a real pleasure to have you all in my committee. I would like to welcome you all and thank you for coming to my defense presentation. My defense presentation is entitled Example Guided Image Editing. And as the title suggests, we're going to talk about images and how we can edit images. We are living in a digital world. This means that there is a massive image and video production. An image, what is an image? It is more than just a set of pixels that represent a certain content, right? It is more than that. Images can tell stories, they can express emotions, they can be pieces of art. Of course, such images can have these purposes if they are well edited, if they are of high quality. However, this is not usually the case. Why? Because there are millions of images captured every day, for example, for the purpose of uploading them to social networks. And as users are not photographers, they might experience several issues during capture. For example, such issues might be noise and blur, could be the lack of contrast and the lack of detail, and also they might capture images which are under or overexposed, and this usually happens in outdoor scenes. So what do people do if they experience such issues? They might turn to Photoshop, GIMP and other softwares which provide useful tools to edit an image. However, they really need to put in time to correct images and they need to be somehow familiar with the image processing tasks to do so. So that's why users turn towards automatic ways and faster ways to edit images. And let's go back to social networks. For example, they provide a set of filters to edit an image. These are very basic filters which take the input image and apply a color theme, predefined color theme on the input image. However, as I said, these are basic techniques. And research is now focused on more advanced and more innovative techniques for image editing. Such techniques, for example, need to enhance the quality of images, make an image well-exposed image without any degrading factors as blur and noise, and also they need to take care of the image stylizing. This means that they need to take into account the image, the user intent and expectation. To do so, we might study some semantic and local features. And as I said, it is really important to go towards automatic ways and faster ways because this is useful for the users. So, a branch of image editing is example-guided image editing. There we have an input image and an exemplar image. Why do we have an exemplar image? Because this could actually really easily define the user's expectations. The exemplar image could be any image, any stylized image. It could be a flash image or a near-to-infrared image. And any other image, that depends on the purpose that we have, on the application. And by having an exemplar image, this means that we can extract additional information from this image and we can make the methods more robust and automatic. And this could be used for a lot of image applications, image processing applications. So this thesis is basically connected to, focused on image editing. And the main contributions of my thesis are the following. We contribute to the field of color transfer, to the field of high dynamic range imaging, and to the field of guidance filters. So more specifically, in terms of color transfer, our contributions are the following. first we built a local Kawa transfer, which takes into account mixture Gaussian models. Then we go further and we consider multivariate generalized Gaussian distribution as a new distribution, and we compute a transformation which is then applied to Kawa transfer and to other applications as well. We also focus on another distribution which is called beta distribution to explain the Kawa and light distributions in images, and we propose a new transformation. And then we propose the first perceptual metric to evaluate the quality of Kawa transfer methods. So far, these methods are focused on low dynamic range images. However, we have extended Kawa transfer also to high dynamic range images. Speaking of HDR images, we can now create HDR images from two low dynamic range images, flash and non-flash images. So this is the main contribution of this work. And finally, we have the perceptual guidance filter, which basically can be applied to a lot of image processing applications, not only to Kawa transfer, but to image denoising, texture transfer, mask refinement, and so on. Due to lack of time, I'm not going to talk about in details the contributions in blue. However, you can find them in the manuscript, and if you have questions, please feel free to ask. So first I'm going to talk about the main contributions of the Kawa transfer, our main contributions. We are building a local Kawa transfer method. So what is Kawa transfer? Kawa transfer methods take an input image and build transformations to transfer the colors, to modify the colors of an input image according to a target image. Finally, these methods obtain a result which resembles the colors of the target image. Let us see the progress of Kawa transfer methods over the years. So first, Reinhardt et al. Have designed a method which is a global method. It takes globally the color and light distributions and builds a 1D linear transformation. This linear transformation basically takes into account a diagonal transformation matrix and also assumes a Gaussian distribution for the color and light distributions, or the global light and color distributions. To go further, PT et al. Have taken into account the correlation between channels, so they built a 3D linear transformation. However, this time this linear transformation is a result of solving an optimal transportation problem. These two methods are global methods. This means that they take into account the global color and light distributions to build their transformations. However, there exist local methods which cluster the images into regions. For example, Tai et al. Have proposed a 3D clustering. And then what they do is that between each cluster they perform a 1D Kawa transformation. Later, Boniu et al. Have proposed another type of clustering according to the luminance channel. They cluster the images into three luminance bands. And then they apply a 2D transformation only on the color channels by excluding the luminance channel and applying a histogram matching on this luminance channel. So we have experimented with these methods and we can list some limitations that we have found out. First, when we talk about global methods, there is a semantic color inconsistency, we call it. This means that sometimes when there are two different colors in the input and target images, we might end up with an image which does not represent the target colors as well. This could be explained by the fact that we have a Gaussian distribution. These global methods assume a single Gaussian distribution, which is in practice not true, as sometimes we might have a mixture of two or more distributions. Local methods go further and they cluster the images into regions, but they assume exactly the same components for the input and target images. Also, they don't take into account the colors for the clustering process. So we might ask, what if we took the colors? As we can see from this example, this is a very valid question. Finally, one final limitation is that sometimes we might obtain over or undersaturated results, such as these, and this might happen because we have the luminance into the transformation. So when we exclude the luminance, we might improve these results. That's why we propose a new local method. Local method which now clusters the images according to the main feature in the images and performs a 2D linear transformation only on the colors. And finally, performs a chromatic adaptation transform at the end. So now let us see more about these local methods. This is the flow chart. What we do first is we have the input and the target images, and we classify them. We classify them, why? Because we want to find which is the main feature in the image. We consider color and light in these cases. So we have two classes, light-based images and colors-based images. Our classification is automatic. This means that we carry it out in the LCH space, and what we do is that we automatically extract the non-gray pixels first. We build the hue histogram of these non-gray pixels, and we're searching for significant color peaks in this hue histogram. If these color peaks are more or equal to 2, are more than or equal to 2, then we know that the color information is significant enough, as you can see from the example. So these are color-based images. Otherwise, when the number of significant peaks is only 1, then we have only one color cluster, and we consider the luminance to cluster the images. So these are light-based images. So now that we know which is the key feature in the images, we can go on with the clustering process. So we have two different clustering, let's say, policies according to the type of feature. If we have light-based image, then we cluster the image according to the luminance channel. So we have 1D clustering. Then if we have color-based images, then we take into account the luminance and the hue, because as you can see, this distribution distinguishes very well the color clusters. And we have a 2D clustering. As you can see here, now we have the clusters, which are actually Gaussian clusters because we assume a mixture of Gaussian distributions to cluster the images. So what do we do next? We map the targets to the input clusters. How do we do that? We have designed 4 mapping policies. So each time our method selects only one policy out of these 4. First, we have light to colors. This means that what we do is we are trying to find the coldest color in the target image and map it to the shadows of the input image. And then we find the warm color in the target image and map it to the highlights of the input image. Why do we do that? Actually, this is very natural. We can find it in nature. When the sun illuminates the highlights, we can say that the highlights have warmer color than the color in the shadows. Also, this is used as an artistic effect. When the image is overall dark, photographers might use color to highlight, to indicate shadows by using cold colors, and to indicate highlights by using warm colors. So this is used as an artistic effect, as I said. So these are the 2 observations that this policy is based on. The next policy is colors to light. So this is the inverse policy of the first one. So it is again based on the 2 observations that we have already seen. Then we have light to light. Here we map the shadows to the shadows and the highlights to the highlights. So this is quite intuitive. And finally we have colors to colors, where we first find the closest colors and we map them together. And then the second closest colors, we map them together, and so on. So this is also intuitive because users would expect that the closest colors would be mapped together. Then, once we have mapped the target to the input clusters, we continue with the transformation. The transformation which is applied to the pair of corresponding input and target clusters. So what we have here is that we are using actually a linear transformation. A linear transformation which takes into account the mean of the input and the target clusters, and also takes into account matrix T. So this is the transformation matrix. How do we find this matrix? How do we compute it? There are many different solutions to compute the matrix T depending on the assumptions that we have. We are computing it using the Monch-Kantorowicz transformation. And we can actually find this transformation is built under the assumption that each cluster is a Gaussian cluster. But we have this assumption. So we can compute T using formula 3. And this formula actually takes into account the covariance matrices of the input and target clusters. We compute the color transformation in the 2D space, only on the chroma channels of LAB color space. We exclude the luminance. And what do we do after we exclude the luminance? we are performing the chromatic adaptation transform in a local way. I will give more information about the chromatic adaptation transform later in the presentation, but for now I will just tell you that we are trying to adapt the colors of the image that we got after the transformation to the target colors. So here is an example to see what is the purpose, what is the benefit of using chromatic adaptation transform. This is the image after the color transform without applying anything to the luminance channel. And here is the image after applying histogram matching on the luminous channel of image A. You see that the image is quite unnatural. Once we apply the chromatic adaptation transform, the image becomes more natural and closer to the target colors. So here are more examples obtained with our method. The first example takes into account light-based image and colorizes it according to a color-based image. You can see that the obtained image is actually quite natural. The same effect could be obtained with another type of policy, colors to light. Again, we have a natural image which has the same dominant color as the dominant color of the target image. Then we have light to light. Here we have two images with a single dominant color, and what we have here is that we have preserved the contrast of the input image. So the image looks quite natural as well. And finally, a pair of images which we have already seen, and now we can see that the result is colorized correctly. The foreground and the background are colorized in the same way as the target image. Finally, a classical example used in many papers. What I want to point out here is the following. It is really important to choose the right policy, because if our method if we had chosen light to light, then we would have obtained this result. However, our method automatically chooses the right policy, and that's how we improve the quality of the result a lot in this case. So to evaluate the results of our color transform, we have users to evaluate results of both state-of-the-art methods and results from our method as well. We have asked them two questions: whether they found the matching colors between the result and the target quite satisfying, and whether they liked the result or not, whether they found it pleasing or not. So for these two tasks, we have computed two scores, style score and aesthetic score. And here in blue, you can see the score, the distribution, the box plots for our method. And you can see that in both cases, we outperform the rest, the other four methods. So to sum up, here, in the first part, I have presented a local method which uses Gaussian mixture models. We have designed four mapping policies which improve the quality of color transfer methods, and we have considered two features, color and light. Now, let us ask ourselves several questions. Can we consider more features than color and light? What if we considered a vector of features? A vector of features such as image gradient, contrast, and many more. How can we describe these vector features? Is the multivariate Gaussian distribution enough? To answer this question, let us go back to our timeline. All these methods consider a mixture of Gaussian distributions or a Gaussian distribution. And this is actually a subclass, a special case of the multivariate generalized Gaussian distribution, or MGGD in short. So what is MGGD? Here is the density function of MGGD. MGGD has three parameters: the covariance matrix, the mean vector, and a new parameter called shape parameter. So by fixing this parameter, we can obtain the density function of the multivariate Laplace distribution or the multivariate Gaussian distribution. So why is this important? Because we have another degree of freedom. And this is important because we can describe wide range of distributions. Not only Gaussian and Laplace, but somewhere in between. Also, when I talk about a wide class of distributions, we talk about heavy-tailed distributions. So we can describe heavy-tailed distributions much better using the MGGD. Why? Because we have a heavy-tailed distribution in blue. And you can see here from the tails that the Gaussian distribution in purple does not describe well the tails. Neither does the Laplace distribution here in green. However, the MGGD in orange describes the tails much better. And this is important for image distributions. Why? Because we can describe there is the potential to describe a wide range of image features, including image gradient fields, because of the heavy-tailed distributions. So, if we want to transform one vector of features into another one, then we just have to transform one MGGD into another one. But then how do we do that? There isn't a transformation in literature to do that. So what we do is that we are proposing a transformation. Here is our general flow chart on the left-hand side. We have an input distribution, a target distribution. On the right-hand side, you can see 1D example, just for illustration. We first perform the Moshko-Torowitz transformation, which we saw in the beginning. And we compute the distribution. However, you can see that this intermediate distribution does not have the same shape as the target shape. So we perform a second step to transform this shape parameter into the target shape. Let me give you the general idea of the second step. What we have here is W, which is the variable obtained after the first step, after the Moshko-Torowitz transformation. This W is actually an MGGD which has the same mean and the same covariance matrix as the target mean and the target covariance matrix. But the shape parameters are different. So we want to transform the beta parameter, here the shape parameter, the input one, without modifying the mean and the covariance matrix. So how do we do that? There isn't a transformation in literature for doing that as well. So how do we approach the problem? We approach it by using the stochastic representation of the MGGD. Here in equation 8, you can see the stochastic representation. We have two variables. These are tau W, and this variable, the distribution of this variable is known, and it depends on the shape parameter, on the input shape parameter. E is also known, and it actually is a uniform variable, and it does not depend, its distribution does not depend on the input shape parameter. So what we do is that we actually transform the distribution of tau W so that now the new distribution, the transformed one, depends on the target shape parameter. So this is the general idea of the second step. And this is how we are able basically to transform the shape parameter, and now the resulting distribution is close to the target distribution. Now let us see some applications to image processing. First we have gradient transfer. Gradient transfer, where we have an input gradient field and we modify it according to a target gradient field. We compute the target gradient field from any target image. Then what we do is that we transform the input gradient field by using our transformation, and then we are recovering an image, F, an output which is as close as possible to the input image, with a gradient which is as close as possible to the modified input gradient. And here are some results. What can we do with that, with the gradient transfer? We can blur an input image by using a blurred target image, and we can sharpen a smooth image by using a sharp target image. So here the images could be any images that the user chooses, and they could only be grayscale images, as we can see from the example. Also, what is the importance of using the second step, you might ask? Well, here's an example. We have a target image which is a very detailed image because it is a painting. When we perform our transformation, what we compute is again a detailed image. So we sharpen the input image. You can see here is the first example. This is after our MGGD transformation. When we perform only the first step, only the Moshko-Torowitz step, then we cannot sharpen the input image as much. So to perform a gradient transfer, we need the MGGD transformation. Another application is the 3D color transfer. Here we perform the color transfer in exactly the same way. So we are using linear transformation. However, here, instead of using T, which is the Moshko-Torowitz transformation, we are using our MGGD transformation. And here are some results. We are comparing our result to result by Pitié et al. And we can see that the two results are quite similar. However, our color is a little bit better, is closer, a little bit closer to the color target. However, we can conclude from this image and many others that we have that in terms of color transfer, our method performs at least as good as SPT et al.'s method and state-of-the-art color transfer methods. Global color transfer methods in this case. Then here's another example. We have an input image, which is enlarged here. We perform the color transfer and we obtain this image. Now, what else can we do? The target image is a detailed image, so we can perform also a gradient transfer. So when we do that, we obtain this image. However, we are doing that in the 5D space, so at the same time we are transforming the color and the gradient of an image. Again, the difference 3D and 5D, much more detailed image. So now we have presented the transformation of the MGGD. This is our proposed transformation, but we have also worked with other distributions. As I said, the beta distribution. So we have proposed the transformation of the beta distribution, which I'm not going to present here. However, it has also applications to color transfer. Moving on, the example-guided image editing can be used for color transfer, as we saw, but it can also be used to create HDR images, high dynamic range images. So, high dynamic range images, as you know, they represent the entire luminance range that a person can experience. So we have extreme dark, from extreme dark to direct sunlight in a single image. How do we measure the luminance range of these images? We compute the exposure values first, as logarithm at base 2 usually, of the absolute luminance, and then we compute the f-stops. So these are the maximum exposure value minus the minimum exposure value to compute the luminance range. So for example, low dynamic range devices have up to 8 f-stops as a luminance range, and low dynamic range devices have more than 8 f-stops. How do we create HDR images? We can create them using LDR images, using a set of multi-exposure images. So the user takes a set of multi-exposure images where they can recover details at every single exposure value, and then the users can merge the images by using the camera response function. The camera response function basically gives the relationship between the exposure values and the discrete luma values up to a scale factor, and it could be computed from the multi-exposure images. How do we do that? We recover the luminance or the radiance, the same, by using the reciprocity property of imaging systems. So we have the luma values, which are a function of the absolute luminance and the exposure times. Once we inverse equation 12, we compute Li, which is the absolute luminance, the radiance. However, these multi-exposure methods have some limitations. Such limitations are, for example, the fact that when we take multi-exposure images, we might need a tripod to avoid misalignment. Also, when there's a moving object in the scene, ghosting artifacts might appear, so these ghosting artifacts need to be removed after that. And also when we have dark environment scenes, there might be noise in the shadows, this noise is transferred to the HDR image, so we need to take care of this noise. So what we are proposing now is to do something different. Instead of using multi-exposure images, we are using only 2 images. A flash image that recovers, that contains the scene details, and a non-flash image which represents the scene ambience. Instead of knowing the CRF in advance, we compute it, we mimic it using a brightness function. And finally, instead of merging the multi-exposure images that we have taken with the CRF which we know, we are just computing ourselves multi-exposure images and we are merging them using the CRF which has been mimicked. Here is the main flow chart. What we do first is that we denoise the flash and the non-flash images. Then we have the 2 main steps. We are performing brightness correction and iterative bilocal CET to compute multi-exposure images, which we then merge in the classical way, as we saw previously. We denoise the input and the flash and the non-flash images in this case because they might be noisy. And we're using the bilateral filter for the flash image and the guided filter for the non-flash image because the bilateral filter is not reliable for dark environment scenes. So it is not reliable for non-flash images. Then what we do is that we're taking the denoised non-flash image and we are correcting its brightness. So we're choosing to compute the brightness and to correct the brightness in a step because actually the idea of the brightness correction is that we want to mimic the CRF using a brightness function. And this is quite natural thing to do as you think about it because the camera at different exposure times gives us an approximation of the brightness of the scene. So we are trying to do exactly the same thing here. We are computing a brightness function which is a gamma function. The gamma value of which is a function of the maximum brightness of the non-flash image and the parameter p, which we can vary and obtain different brightness images, as we can see here. Once we vary the parameter p, we obtain different brightness images, non-gray, grayscale images. And then to compute the color images here, we are just inversing the process by using the non-flash image. So we might ask ourselves, okay, why can't we merge these images and compute an HDR image, right? Well, if we do so, we can do that, but if we do so, we might not recover important details in the shadows, in the highlights, and so on. This is because we don't have additional information. We have only the non-flash image. So in this sense, we are using additional information from the flash image. We are computing an iterative bilocal CAT. So we have already seen chromatic adaptation transform before. Now let us see more details about the chromatic adaptation transform. We have a global chromatic adaptation transform first. So in terms of flash and non-flash, we are computing first white images of the flash image and the non-flash image. We are computing the ratio between the flash and the non-flash images, which in this case are constant white images, so they are the same for all pixels. And then we are computing the von Kris normalization from equation 14. Here we can conclude that kappa, the ratio of white images, is constant. The local CAT does something more. So in the local CAT we compute the white image using the flash image. So basically kappa now, the ratio of white images, is a function of the flash pixels. So now we are proposing to do something more, to do the same for the non-flash image. And we are computing the non-flash white image using the non-flash image directly, and kappa is a function of both the flash and the non-flash pixels. Let's see why this is important. This is important for our case because when we have the bilocal CAT, we apply the bilocal CAT on the flash image using the non-flash image. So when we do that, we transform the flash image into this image, which has almost the same illumination as the non-flash image. But also, using the bilocal CAT, we can recover details, which is the most important thing, basically. You see the non-flash image here, the gamma-corrected one. You don't see any information in the shadows. Once we perform the bilocal CAT, we recover the information in the shadows. So that's how, when we perform the bilocal CAT between every single image here in the brightness exposure and the flash image, we are computing the set of multi-exposure images, which we then merge, as I said, in the classical way. Let us see some results. We have two images, the real HDR and our result, which are tone mapped for visualization purposes. So we are comparing our result to HDR image, which is obtained using 5 multi-exposure images in this case. And what we can see here from the histograms is that we recover the luminance range, and also both histograms are similar. We are also using the HDR VDP2, this is a metric, to see whether there is a difference in the luminance between the two images. And you see the blue areas here, there isn't a significant difference for these areas here. We have some red areas where we find difference. What is this difference due to? We can see another example here. We have red regions over here, and let us look into these regions to see what's happening. For the real HDR image, we don't have as many details as the details that we recover using our method. So another property of our method is the fact that we can actually automatically remove shadows and reflections caused by the flash. So here you see the flash, the shadow and the reflection, and these are automatically removed using one transformation. Also, we can use our method not only for HDR images, but also for LDR images to improve, to enhance the LDR images. So in this case, you see two results of our method that are obtained using different tone mapping operators. Of course, there are other methods that do exactly the same thing, but these methods actually do not perform a single transformation, but they separate the images into base layer and detail layer, and it is quite different. However, our method can compare with these methods. So that is how we know that how we can create HDR images using two LDR images, flash and non-flash images. We saw the bilocal CAT, which is also very important. It has a potential, this bilocal CAT. And what we did in our final contribution here is that we built a filter embedding the bilocal CAT in this filter to use it for a lot of different applications. As I said in the beginning of the presentation, for texture transfer, for mask refinement, denoising, deblurring, and so on. So to sum up, we have seen new Kao transfer methods. Kao transfer methods that assume mixture of Gaussian distributions, beta distributions, MTGD, and so on. In all these Kao transfer methods, we have a target image, which needs to be provided by the user. So how can we go further? We can try to remove the target image because it might be a difficult job for a user to choose a target image themselves. So we might just, so the user might want to choose just a style or a class of images. So we might use an abstract image to do so, to represent a class of images. Then we might go further and we might consider non-photorealistic style transfer, because so far we have presented only Kao transfer for photorealistic purposes. Then we have seen how we can create HDR images using flash and non-flash. This work has, however, one limitation, and this is when the contribution of the flash is not significant, and this usually happens for outdoor scenes. We cannot recover many details using our method. So what can we do? We can try to replace the flash image, for example, with a near-to-infrared image, and perform our method as well. Or probably, in the future, we would like to extend our method for creating HDR images using a single image, which is a highly constrained problem, but this could be tackled in the future. So finally, my thesis has resulted in one journal paper, 4 international conferences, and 2 submissions, 1 journal and 1 conference. For the journal, we have already 2nd round of revision. So I would like just to take a moment here, because all this work has been done under the supervision of Remi, Olivier, and Kadi. So I would just like to take a moment to thank them, because I have learned quite a lot from them. So to thank them for their patience and for being always so helpful with me. So, and then I would like to thank you all for presenting, for assisting to my presentation.
Donc on va passer aux questions. On va commencer par les rapporteurs. Et donc on va passer Joël, qui est professeur à l'université de Cozot.
Okay, merci. First, I want to say that I really appreciate to read your manuscript, and I am quite impressed by the quality and also the quantity of method that you work on and you propose. It's really impressive for a PhD. So.
Thank you.
And we see that in your presentation, as you cannot present all what you have worked on. So.
Yes.
So I will concentrate most of my question on the color transfer, because this is more of my specialty, and I will let Alan probably discuss the HDR part. My first question was on the first part on the clustering. How many clusters in general you have for color images? It's like it's more or less 2 or 3, or can it be a lot of clusters, or?
So that would depend on the image, of course, but we have found out that actually 2 to 3 clusters. It is usually this is actually an automatic process. As I said in the beginning, we are finding significant peaks, so usually they are 2 or 3. So we are setting the number of clusters to 2 or 3, and this is done automatically. Sometimes in a very colorful image, for example, if you have an image of several quite different colors, you might have 4 or 5, but usually it is 2 or 3, yes.
Okay, and the choice of the clustering algorithm, I was thinking like you could use also mean shifts or other kind of clustering?
You mean another clustering technique? We have used the expectation maximization in our method. However, we can use another one as well. But the thing is that we want our clusters to be as close as possible to the Gaussian distribution. And to make sure that this happens, we need to use EM.
Okay. And so if I understand well, when you have a different number of clusters on both images, you just keep the minimum number of clusters?
Yes.
The matching?
Yes.
So it means that if you are working on light, one light-based image and a color-based image, you will never have more light than 3 clusters, or how do you?
Yes, you're right in this case, because in a light image, you can have 3 clusters: shadows, midtones, and highlights. So in this case, you might have up to 3 clusters, but you might have 1 cluster, or you might have 2 clusters as well.
Okay, and in the manuscript you showed some failure cases, and it's not clear for me why, what was not working for these cases actually. So do you have any idea of?
In this case, we said that it is a failure case. Why? Because the users did not expect this result. So even though, as I mentioned, the policies are quite natural because of several observations, sometimes we cannot have a general method. So users sometimes might expect something completely different. But this is connected to the fact that, let's say, the foreground and the background are in some colors which are not exactly natural for foreground and background. So
You don't exactly know if there is a problem, like sometimes it's not a good policy that is used, sometimes there is not a good number of clusters, or so you just, I mean, for the limitation, it's not clear where if there's something missing in some part of the pipeline.
Actually, it is in the policy, because probably yes, the right policy has been chosen for a pair of images. However, this policy might be not the correct one for this pair of images. Sometimes, yes. So a different type of policy might have been a better choice in this case. So, yeah.
But I know that this is very hard to evaluate the correct answer, and this is
yes.
subjective. So
yes, it is quite subjective.
I need to. I was a bit. I was looking forward to see if your conceptual evaluation
yes.
could be applied to all of your work. So, for example, the chapter 8, where you devise a conceptual metric, you haven't used it to evaluate your contributions. So, do you have tried it, or it was a question of time? You didn't have time to.
Actually, yes, the perceptual metric is specially designed for color transfer. So for chapter 8, it would not have been appropriate, because what we do is that we apply to texture transfer and.
No, I mean the chapter 8 is the chapter of the perceptual.
Yes, the perceptual metric for color transfer. Yes.
Yes. So my question is, would have have you tried to use it to your own contribution on color transfer?
On color transfer, yes. Yes, we have evaluated, for example, the first color transfer method, basically, but most of the images were used actually in the user study. So.
And you haven't tried for the other?
No.
Is there a reason for that, or just was a bit surprised that? Just a question of maybe a time. You don't have time. I don't know.
Yes, I guess that. Yeah, it was that because yeah.
Okay. And in the chapter on the MDGD transform, you said in the conclusion that it could be nice to take into account the gradient direction.
Yes.
So do you have any idea to do that? Is it?
So the gradient direction, basically this, I have been thinking about doing it in the transformation as well, but in a way modifying the transformation. Because what we have in this transformation is a vector in the stochastic representation, another vector, I have presented this one, another vector which is basically could be used, I think, for the direction. Let me just go back to the stochastic representation. So here, we have another vector, which is E, which is uniform variable. So maybe there's something to be done with this variable, and probably by using some kind of a filter before that, so that we can have actually some kind of a direction to go to. And I have been thinking about doing that for non-photorealistic transfer, because it would be interesting, for example, to model the strokes of painting and then to transform an input image according to the modeled strokes. Yes, but yeah, this is just an idea for now. I haven't had the time to explore it so far.
But I think it would be interesting to see
yes.
what we can do with that. So I come back to the chapter on the perceptual metric. Mm-hmm. So if I understand well, mm-hmm. you use two criteria, one of the color matching and one of the aesthetic quality of the matching.
Yes.
But at the end, you make a mean of these two criteria, right?
Actually, no, for the perceptual metric.
He's saying to me that I should...
So you're asking about this one or the perceptual metric, because they are...
The chapter 8.
Okay, yes. So probably I can show something more. So basically, yes, here. So this is another user study that we have carried out. It is not the same as in the first part where we have carried, yes. So here we are, yeah, exactly, we are combining. We are asking the user a single question. So they need to evaluate their expectation. The thing is that we have the input image and the target image, and then we show the result after 5 seconds. And then the users have the time to, in a way, try to expect what the result would be. And then they're asked to evaluate their expectation in this case. So yes, both criteria are in the same time combined, but not like separately and then computing the mean, but combined in a single task.
Okay. Because it wasn't very clear for me in the writing. And so I was wondering if because I was thinking that, okay, these two criteria are very hard to separate.
Yes.
Because somehow if it's not aesthetic, then maybe I will think that there are not the right colors, or I don't know, they are probably mixed. Okay.
Yes.
So, okay.
Yes, there is a correlation, definitely, between them.
Because you say that you give a triplet baseline just to,
yes.
to calibrate.
Yes.
And I was wondering if it would make sense to have like two baseline, one with the correct color matching, but like visual artifacts to try to separate between the quality of the colors and the aesthetic quality. Maybe it would give some insights on how people are evaluating the results.
Yes, yeah, that's an interesting idea actually. But I think that what we have found out from these experiments is that basically people are reluctant to give high scores to an image which is degraded image. Yes, so yeah, they're correlated. For sure, if the image is not of high quality, if it has artifacts, then the image is not good in terms of color transfer as well.
Yeah, so you would say that the aesthetic quality is on top on the color transfer. If there are some artifacts, whatever you can do, you won't have a high score.
Exactly. However, if the input image is a degraded image and then we get the same image basically after the color transfer, then it is okay. But if the color transfer causes some artifacts, then it is not okay for the users. So they would not give high scores for sure. And we have actually in the manuscript you have. Let me show you. You have the importances, which are basically these ones. You see that the SSIM here has the highest importance for the color transfer.
I found this chapter very interesting, and it's, this is a hard question, so. And maybe just to finish, in the future work section, you discuss about an idea of giving abstract images as a control way to control the target image. Could you develop a bit on that, because I find this idea very very interesting.
Yes, basically this is just a general idea, just a thought that probably we can use. What a user wants. They don't want just to choose an image, because when they choose an image, then okay, we will perform the color transfer. But if they choose a similar image, an image which has almost the same style, like we can perceive the style and we can say as humans that the two images are of the same style, right? So if the users choose a different image of the same style, then the color transfer would not give the same result. So we would like to solve this problem in a way. So how can we do that? Probably have an abstract image for a style, rather than having the user choose a target image. So this is the problem that we are actually trying to solve, but it is just a general thought that something in the direction that we might go to in the future, but for now it is not so clear. We just have that idea.
Because I was even thinking that maybe for some specific cases you could even let the user draw something that could give the target. I don't know if it makes sense, but maybe for if you want just to add some blur, for example, maybe you don't just have to draw some blurry thing, or I don't know.
Yes, for example, there have been methods that are using color palettes. Then the user chooses just a color palette. And so this is in a way an abstract, okay, not an image, but a color palette in this case. So we are thinking in this sense, in a way, but not only to have a color palette, but more like a style thing. It is, again, a very difficult thing to do, and it is not so, it is a new post problem in a way, so, yeah.
These are all post problems. Okay, thank you.
Thank you.
Deuxième rapporteur, Alain Meur de l'Université de
Okay, thank you very much. Thank you for a very interesting and very informative presentation and a really well detailed thesis. Just a few questions. One question on color transfer. I guess I'm interested more into video, and if you want a target image but you had a target video and you input video, would you have any temporal artifacts over the different frames of the video? How would you go about ensuring that the whole video had the same style as the input, as the target image?
This could be done in different ways. What I can think about now is, for example, using, if you have single image and a video, right? Yes. So, for example, performing a color transfer between the first frame and the image, and then performing a color transfer between the colorized frame here and the second one. So somehow, probably this would help with the artifacts.
Okay, thank you. Okay, then on to HDR, which obviously I know a bit more about. So Flash is very interesting how to use with HDR. I mean, one of the big problems with Flash, two big problems. One is if you take a picture of a mirror, you get a very big flash, or you get the red eye is also one of the big problems with people always get the red eye. Does your method deal with such, you showed the example in the thesis, but it was quite a small flash artifact, but sometimes the flash artifacts can be quite, you take a picture of a mirror with a flash.
Yes.
And so the red eye is always a big challenge. You always end up with the people looking like demons because they've got red eyes. Can your method cope with both those cases?
This is a very interesting question actually, because I don't think that we have actually tried an image with red eyes. So it is really interesting to see if it works. So far, for the images that we have investigated, that we have worked with, it turns out that, for example, for the flash reflections, it is, so there's a trade-off sometimes. You might not transfer the whole illumination of the non-flash image, but you might remove the flash reflections. However, you can like iterate a lot with the bilateral filter, and you can remove everything. So you can remove the flash reflections, probably the red eyes, because I'm quite sure that you can remove red eyes, but you might lose some details. So there will be a trade-off for sure. Yeah.
Okay, and then the displays. I mean, you have an HDR display here. I mean, when you did your evaluations, you mentioned briefly that you used the HDR display. What was, if you had the real HDR image, well, the multiple exposure one, and your one on the same HDR display, could you see any real difference perceptually rather than once it's been turned out on print? What did you do a perceptual study on that?
An official perceptual study, no. But we had experts here. We have looked at the images. We have compared them, and actually, then after that, we used the HDR VDP2. So we are in a way in agreement with what the metric says. Because yes, we could see that our method can recover more details for the images that I've shown. And yes, and we could see that with 5 images. Of course, if we use a lot of images, we might be able to recover the details in the shadows. But for 5 images, we have actually in the HDR display seen that we don't see the details in the shadows, not as clearly as our method does. So we have done, yes.
But do you think the human would see those details as well? Because if HDR is trying to mimic human vision, would the human see those details? So obviously Flash might give you far more detail than human vision might see in that situation.
Yes, also this is a very good question, because in a way we don't know exactly what the ground truth is. Even if we take a lot of multi-exposure images, as you said, this might not exactly be the same thing as the human eye sees, after all, right? Because you might not notice the details in the shadows.
These labels, for example, you might not be able to see them because of the contrast on the scene.
Yes, exactly, yes. So we had a problem with that, how to exactly know which one is the ground truth. So we don't say that our method is the best one, but we say that, okay, we can recover details. And this might be important, especially if we are using LDR displays. After tone mapping the image, we can see details. So probably users will be happy with that, with having more details in the image anyway.
And final question, so I mean, you use a flash, but I mean, you could just as well use a very bright light. You don't have to use a flash from the camera. So, and you could put multiple lights, of course. I mean,
yes.
So maybe that's your solution for the outdoors, is you have a very bright light and you take your picture and you take your flash. Do you think this would work with video?
With video, yes, we have made some experiments, as I mentioned in the manuscript very briefly at the end. So yes, it works with videos, but for now the frame rate is not high, so there are artifacts in the video. Yes.
Good, thank you very much.
Donc on va passer aux examinateurs. Marcello Bertalmio de l'université de PU.
So very briefly, I completely agree. It's a great presentation and astonishing amount of good work. I was surprised.
Thank you.
This could fit in one thesis, so congratulations on that side. So, okay, I have several questions. Starting with the style transfer, one of the assumptions that you make is that highlights are associated with warm colors.
Yes.
But you can have artificial light sources which are cool and that produce highlights. I'm thinking of urban scenes at night with cool. So would that break your style transfer?
That would depend. because we're actually trying to find the warmest color in the scene. So if the warmest color is actually a cold color in the image, you see what I mean? If the blue color is actually the warmest color that we can see in the image, let's say that there's purple as well, there is blue and purple, then this would not break the policy in a way, because we still would, do you see what I mean? We would still map the blue to the highlights and then the purple to the shadows.
Oh, I'm not sure. See that because you could. I'm thinking you could have cool highlights and a warm candle there, which is not shadow.
Okay, I see. Okay, this is for the target image.
Yes.
Yes, and that then you have to vote for an input image. Let's say you have a light image.
Yeah, for I don't know.
Yeah, I haven't been thinking about that actually.
Just a thought. So.
Yes, thank you.
No. So in the maybe you can go to the in your slide where you have the color-to-color case with
Yes.
the flowers example.
Yes. Color to color.
Yes.
Here.
So in the, I think overall it's a fantastic result. I do see some fringes, like blue-violet fringes on the bottom right. So why do you think that happens, and do you think that could be solved somehow?
So you're talking about here on the flower petals?
Yes.
Yes. Okay, so yeah, you're not the first person that actually sees that.
Oh, I'm sorry.
No, that's very good, because yeah, users can actually see it, and some of them thought that this is not exactly the best result that there might be, because of these in a way artifacts.
Okay.
So how I can explain that? We have the clusters, but we also have an overlapping between the clusters. So this could be explained by the overlapping, because you have green and you have in a way light purple, yes, pink. So basically, when you have an overlapping, the overlapping is right here exactly.
Okay.
Between the clusters. So this is why this is happening.
All right.
Yes.
And have you thought of something to try to correct that?
No, actually, no, I haven't.
No, it seems like a tough problem. So related to that, I'm sorry I'm pointing this out. Don't take. I think your work is fantastic, but I think there are some questions I'd like to ask you which are related to the limitations of your work. So
Yes,
please don't
yes.
take it back. So related to that, so in page 95 of your thesis, I don't know if you have the PDF for your thesis
No,
there.
I
No?
don't.
So there's maybe I can tell you what.
Okay, yes, I think.
Yes, I
thinking.
can have it here in color. So in that's figure 7.8, in the bottom row, you
Yes.
have also some flower examples, and
Yes.
you have some artifacts
Yes, I can
in
see.
your result. In the top part of your result
Mhm.
of the flower, there are some artifacts in this like round.
Yes.
Okay.
Exactly. Yes.
So I think that's probably different from this. I mean, caused by a different problem. But maybe do you think you could fix that using the same sort of approach that PTA used to go? You know that PTA's method has like 2 passes, and in the second part they
The
correct.
green.
Yes.
Right? Yes. Mhm.
So I don't know. Maybe you could use that.
Actually, yeah, probably I can use like in a way a regularization technique
Yes.
at the end. Yes, that could be interesting. Also, something that I could think of is I have an overlapping which has a default value. So the amount of overlap is the default value in my algorithm. So if I change it, I would get a different type of result.
Okay.
So this might be also corrected by using that.
All right.
But also using some regularization, that could be a solution as well.
Okay, thank you very much. Okay, going back to the NDGD in your slide,
Yes.
you show the 5D example for the landscape image.
Yes.
So here, I would argue that there's a color shift here that was not present for the regular, yeah. So here, I very much like this result. And I agree that in 5D you have more detail, but there's a color shift. It's no longer as, well, maybe it's the way I see it. I don't think it's as bluish.
No, there is actually, yes. I think that, especially from the sky, if you look at the sky,
Yeah.
there is a color shift.
So why do you think it happens? Because you could, well, because it's 5D, and maybe you should do the gradient part only on the luminance, or why do you think that that's the case?
Actually, I do it only on the luminance in this case.
Oh, okay. So
yes.
then, so that's why I thought. And then I'm surprised that you get that, right? Because if you change just the luminance, you shouldn't get changes in the other channels.
I'm not so sure because actually I've always got changes in the other channels as well. Yes, because in a way, okay, when we have a 5D transformation, we are taking the correlation. Okay, there's a certain kind of correlation between the luminance gradient and the colors, after all. So I think that this might cause the color change.
Okay, so you say that it's because they're not perfectly correlated in LED.
Yes.
Yeah, okay. Yeah, that makes total sense. So in when you're using denoising, I guess it's for the flash, non-flash work.
Yes.
Why not use a more sophisticated denoising method like BM3D or something like that? So you use the bilateral filter and the guided filter, which seem to work very good, but maybe you could get better results with better denoising. Have you tried better denoising, or it wasn't necessary?
I don't think it was necessary actually,
Okay.
yes, because guided filter, especially for non-flash images, worked perfectly well.
Okay,
And yeah, it was not necessary.
all right. Okay, in the bilocal CAT, your coefficients are local. Okay, so you have this ratio, which is local.
Yes,
And they could get pretty high. I mean, you're doing this ratio, and
Yes.
if the denominator is small, you can get a huge value for K. Does that happen? And if it does this cause problems?
actually, yeah, this is also, let me just go back to, let me go to the slides. Okay, so in this case, right?
Yeah.
Yes. So when the denominator, okay, so yes, this can happen, of course. Especially when the non-flash image, in the shadows of the non-flash image, this could happen. Actually, we regularize that, so yes. This does not cause problem because we regularize it, we take care of it in the way that we have developed the software.
Okay.
So.
But still, they're not aligned. I mean, one of the cool things about your method is that you don't need a tripod, right?
Yes.
So in that case, a small misalignment at an edge could cause that you're dividing by something which is close to black, even after regularization. So I see that could happen. I mean, in this case, there was a tripod. I mean, these images are taken with a tripod, right? But in a general case, I believe that with a small motion, and you take a picture where there's a black object over a white background or the other way around, if regularization, you can have this situation. So I was just curious.
Yes, but yes, this is a good question. But you see, now we are computing the white image. So there's a difference between the image. Of course, if it is completely black, we might get the problems that you are talking about.
Yeah.
But here, if we have only small regions of black, and when we perform in this case, we are computing the bilateral filter to compute the white image. So in a way, we are changing the values. They are no longer black if they're in a small region. But if the region is is big, yes, if the window is big, then we might get some problems. I haven't been thinking about that because I haven't experienced any problems with the images which I have.
Okay. All right.
Yes.
Okay, I don't want to take too much time. Let's see. So when you're using in the flash non-flash case, you're comparing against the case of doing HDR from 5 exposures, and
Yes.
you're saying you get comparable results and better than if you just use 2 exposures.
Yes.
Right? But I think that that would depend on how those 2 exposures are taken. I mean, if they're taken with enough EV difference, exposure value difference,
Yes.
with 2, you should be able to cover the whole dynamic range in most situations. I would think.
Okay. I see.
So it's just the so for instance here, the light coming from the window is so much that the darkest parts, even inside, they shouldn't be that dark.
Mhm.
So just a comment. So
Yes.
I think it depends on how you take the 2 exposures.
Mhm.
So probably you can figure a way out of choosing the 2 exposures so that you can.
Yeah, you can
match
get
them.
like the maximum luminance range that you can.
Yes.
Yeah, I agree with that actually. But one thing that I can think about this approach is, for example, if you have a low and a long exposure. So what we do is you really need a tripod for this case, right?
Yeah.
So this is While in our method we don't need a tripod.
Yes,
So,
no, that's
yeah,
what I'm
but,
saying.
yeah, I totally agree. We can recover the luminance range. So that depends on the exposure values which we would choose.
Yes.
Yes.
A more, a more practical thing is some cameras allow you to take pictures with dual ISO, so you get it. I don't know if you know. So you have like interlaced lines, and some lines have some ISO value, and the other lines have higher value. And then you can take at the same time both pictures, and you have to combine. So that is good.
Yeah, that would work.
So, yeah, I will just wrap things up with some final question. Just quickly. Okay, so that's my final question. In the case of example-guided high dynamic range image editing, you're arguing that it's better to do the color transfer among the HDR images directly rather than using tool mapping because that may cause artifacts. And,
Yes.
okay.
Yes.
So I have a question about that because if your tool mapping method is invertible, then you could think of doing the following. You have your HDR image, apply tool mapping, the same to the reference, do the color transfer there, and if the tool mapping is invertible, you invert the corrected transfer result. And the artifacts that would have appeared originally with the original tool mapping, they should go away when you apply the inverse. So have you tried that? Because they are invertible tool mapping methods. Have you tested that? That would be okay?
No, actually, we have not tested that.
Okay.
But this is a very good idea because now that way you can use a number of color transfer methods basically.
Yes.
And it would be it would be done in the LDR between the LDR images, so it would be faster and more efficient and everything. So yeah.
Yes. That's all. Thank you very much.
Thank
Excellent.
you.
Excellent job.
Thank you.
Merci. Donc, second examinateur, Nicolas Bouatouch, chargé de recherche à l'ADRS au LIS.
So, thank you very much. I was also very impressed by the presentation. There's also a good amount of work, so I have also many questions. You can also maybe like very short answers are fine. But I start with the most important question I believe is for your perceptual experiment. now, if I wanted now, I'm developing a new color transfer algorithm, and I want to evaluate it. Should I redo the experiment, or do you provide your regression model somewhere?
Yes, the perceptual model will actually be available soon, so you can use it.
Okay, nice. I'm also wondering why now with Mechanical Turk and website like that, you can do experiment on like 1,000 people for, it costs a little bit, but reasonably at least. And yeah, instead, right now you did like a small experiment with I think 10 people, something like that. Is there a reason why you didn't use a bit more like a broader scale?
Well, actually, our idea was to use to invite people from the lab. So it was again an online platform that we use for the experiments, but we're using just people from the lab for now. But you are completely right, because if we, of course, put in a little bit more like time and invite more people, this could be like become a really huge user study, and we can even post it online, and a lot of people can do it. But for our purposes, it was not so necessary in a way, because after that we analyzed a lot, because we had a lot of big data set basically, so it was not so mandatory to have a lot of people after all.
So how many data points you have at the end?
So we had like 120 results per method, I think.
Yeah. Thank you. I'm also wondering for your 5D approach for color and gradient transfer.
Yes.
Like colors and spatial gradients are like two very different things. So do you weight them differently? Like if you weight the gradient more, like in your 5D space, if you give the gradients, you multiply all your gradients by 10,000, will it change the result a lot?
Yes, it will change the result for sure.
So what kind of weighting is there right now? How
So
did you weight them?
it was like a weighting of 8, I think I used, just a default value.
Okay, I didn't see it mentioned, but maybe it's...
No, I think it was not mentioned. Yes, I'm just telling you now. I think it was this what I've used.
Okay.
Yes.
I'm wondering if there's not a confusion for the local approach for color transfer.
Yes.
So usually when we say that it's a local method, it means that it's spatially local.
Yes.
Here it seems that the color clusters are performed are determined in the color space. So these are it's local in the color space and not in the spatial domain. So if it's local in the color space and you're doing a transform of the color space, it just means that your overall transformation is nonlinear, but it's not necessarily local. What can I say? Yeah, I just believe that your approach is still a global color transfer. Although you may think that it's local because when you determine color cluster, you see on the screen, you see different color cluster appearing in the image, but I think it's still a global color transfer, no?
Actually, yes, we are clustering in the color space. So on the chroma channels. Actually, it depends, of course, the luminance and the hue. This is what we use. And yes, we use, in a way, we're performing a single transformation between each corresponding pair of clusters, right?
Yeah.
You got that?
Yeah.
So in this sense, it is local. We are not using the spatial location, you're right, in this sense. However, yes, we can see the clusters. When we cluster the images into regions, we can display, we can visualize the clusters.
But if you do, for example, a non-parametric approach, that will just, the only thing that it will do, for example, will cluster the two images into color clusters and then match the different clusters, and then it's still a global, like the method of Pitié, like not the linear Monge-Kantorowicz approach, but the non-linear one, the sliced approach. It finds it's not cluster based, but it finds a non-linear color transformation between the two images. But this non-linear transformation is if you had some clusters before, it would not change anything. And the fact that there are clusters doesn't mean that it becomes local, right? Or maybe we can discuss that a lot. Yeah, maybe I'm not clear. But yeah.
Yeah, maybe we can discuss after that.
But, and then for the peak extraction, so Joël mentioned the mean shift algorithm to determine clusters. But for the peak extraction, you also have a fancy algorithm to try to determine the peaks. And usually mean shift is especially designed to determine peaks in histograms. Like it's a method to determine modes in a histogram. So did you try it, or like wasn't not working well?
No, because our idea was to have only significant peaks, so we wanted to, in a way, correct a little bit this algorithm. So we didn't want to use mean shift directly, but we wanted to work for a certain type of purpose. You see what I mean? We didn't want to find all the peaks, but only the significant ones. That's why we have a new algorithm, basically.
Okay, but did you compare with it or try it?
No, I haven't.
And I didn't see any mention of speed in Meur. Like, I would believe, given that the algorithm, that all your approaches seems to be fast, I believe. But is that the case, or how much time does it take to run all these different algorithms, like from color transfer to HDR and
So yes, they are fast, but that also depends on the resolution of the images. So, for example, the slowest method is if you have the multi-feature transfer, because you take a lot of features, you're computing also, you have the gradient, the screen Poisson equation, so that takes a little bit more time, but usually it is a matter of several seconds.
Okay, now we'll stop.
Thank you.
Thank you very much for a really nice presentation and giving me a lot to read in the train. Actually, normally I can read a whole thesis in a long journey, but I actually need to spend a bit more time on yours. So, a lot of work done, eh? It also means you get a lot of questions, and despite the enormity of your committee, not all questions have been asked yet. So I have a few more, if I may.
Yes.
So the first thing I would like to talk about a little bit is the policies on your color transform. It occurred to me that you have effectively threshold. You analyze an image, and then there's a threshold, and if your image falls on one side of the threshold, it's a light-based image. If it falls on the other side of the threshold, it's a color-based image. And you do that for both your input and your target images.
Yes.
Two thresholds. So now I'm just wondering what happens if I, let's say, artificially create an image that sits just on one side of the threshold and make another one that sits just on the other side of the threshold. Will I get a big jump in my results, or is there somehow smoothness designed in?
I see. Well, that is an interesting question. basically, in this case, the policy that will be chosen would be light to colors or the other way around. So we will just proceed in the way that's being described, and as long as there are two meaningful color clusters in an image, so we are lying on the other side of the threshold, then we can basically segment the image, separate the image into two regions that are the color clusters, basically. So there will be information to cluster the image, and the same for the other one. So we would just proceed in the same way, I guess.
The reason I'm asking is because, like Alan, I'm very interested in video, and you will eventually come across a scenario where the video slowly changes its illumination or whatever is in it, and then you might, with your algorithm, you might swap to a different policy. And then the question is, do I get an artifact, a jump in my video?
Yes, if you perform like frame by frame, if you use one image or two video sequences and you perform the color transfer frame by frame, yes, you would get such color swap. I have tested actually, and we get artifacts, yes.
There's another thing that occurred to me on the light policy specifically. It seems to me that what you call a light policy is any image that has effective distribution may be embedded in the 3D space. So if I have whatever color space I have, a light image is something that gives me a distribution of pixels that lies along a line, effectively, more or less. And an extreme case is a grayscale image where the line would be aligned with the luminance axis.
Yes, yes.
So if I have a light to color mapping, could I not use simply a colorization algorithm?
I guess yes, you could. Yes, I guess you could.
Would your method still hold benefit?
Or colorizing methods. This is something that we have not tested as well. Probably we could experiment, to see. But let me think. This could be tested. That would depend.
I have a question on chapter 6, which is your transforms between distributions.
Yes.
It's just a clarification. So your transform, is it somehow an approximate transform, or is it an exact transform?
It is an approximate.
It's approximate.
Yes.
So have you looked at what happens if I take an image and I transform it, and then I transform it back? Will I get more or less the same image?
And you transform it back. Yes, I have actually. And you don't get exactly the same image, but you get very close, similar to the input image. Yes.
So some round trip performance is
Yes.
Can I ask you to?
Yes.
No, I'm not asking you anything. I was having an question on slide 108.
Okay. Oh, okay, super.